We have with us Dr. Priyanshu Bajaj, Regional Manager for Asia Pacific M4P Solutions, who will be talking regarding the laser powder bed fusion AM process.
Hello, good day everyone. Hello and welcome to AMIC 2021. This is Priyanshu from M4P Metals for Printing. Today I'm going to talk about a very small talk on predictive process development for laser powder bed fusion additive manufacturing. We are Here we are looking largely into the high conductivity metals, but I'll start with the basics and then go forward. Before I start, just a few words about M4P. As M4P or Metals for Printing, we are a company involved with metal powders for additive manufacturing applications. So this, of course, involves the entire umbrella, so DD, LPBF, electron beam, and also binder jetting. As a company, I rather say that we are more so a materials company than a metal powders company. What this means is we start with defining the chemistry. So custom alloys, we have some custom alloys, custom chemistries, which are designed for AM. Even for regular alloys, we give a good hard look at the impurity elements, trace elements, and see how they influence the process and also properties of the AM produced parts, and we define our own limits within them. We try to modify the limits within these standards for standard materials. So, and then of course, production of metal powders, and then selling of metal powders. Of course, it's a bread and butter, but that is not where we end. We then try to support our customers, the teams, and the market with also processing parameters and post processing treatments of these materials. As our offerings, the major offering, of course, is metal powders. But then, of course, we also do material consultation. That is when you have a material in mind that cannot be printed. Traditional example, a conventional example is, say aerospace companies want to print 6,000 series or 7,000 series aluminum alloys. Or when you are a OEM and you have properties in mind, but you don't know which material to go for, there we can help you select a material which can be produced in AM and can fit for your requirements. Of course, there are cases when such a material does not exist, at least in the AM world. Then we try and go back and try to develop a material for you. This is, of course, not a fundamental science that we do, but we take something that we know works from the literature, from what we hear from our research partners, and we take something which is already known to work. So let's say TRL level 2 or 3, and then we ramp it up quickly to 5, 6, or 7, depending on the requirements. Laboratory analysis, I think I don't need to go on much details. Material recycling, AM training is also something we offer, which is basic AM training and material design, machine processing, file design, etc., etc. And special services is again, as a company, we're very designed for custom projects. So when you need something which you do not offer as a standard offering, please get in touch with us, and we can definitely give you a customized solution for you. In terms of portfolio, we have a really large material portfolio. At the moment, I think it's around 57 different materials that we have on offer as standard products. This includes the entire aluminum family, coppers, lots of steel, stainless, maraging, wear resistance, tempering, even soft magnetic, nickel alloys, titanium grades, cobalt, and even some refractory metals. So this is materials like pure tungsten, pure molybdenum, and so on. All our materials are defined and have been adapted to suit different AM systems. Of course, this is required when you think of being a powder particle and how you will respond when you are in a machine. Many things changes in an US machine. For example, you are normally sitting nicely in a bed, a lift, you are lifted up with the platform, and then your only job is to spread on on the build platform. But if, for example, when you are in a different machine environment, say a Renishaw system, where you are placed in a hopper, and now you want to go down. So your first job as a powder particle is to go down, and then your second job as a powder particle is to spread to the build platform. Then again, you can imagine yourself being in a material as a powder particle being in a machine which has a roller type tricoter. So there you want to get stuck to the roller and then be deposited on the build platform. So as you would imagine, these all machines require different kinds of powder particle size distribution, and we do that. We try to offer start parameters for most of our materials, of course not for everything, but for most materials we can offer you with start parameters and also heat treatment processes. But in any case, when you need new alloys, that process is also really fast with us. So we approach the things in a so-called agile development approach. But let's move on to more interesting stuff and start with additive manufacturing or 3D printing. Why is it? What is it? Broadly speaking, many designs we have are now in computer format, a CAD file, and we can cut these CAD file into thin layers, virtual layers, and then using some method, I can convert these virtual layers into physical layers, and when these physical layers combine, over and over and over again, I will get a 3D part. It's very similar to an inkjet printer, where you print line by line by line, and at the end you have a full 2D page. So imagine printing layer by layer by layer, and at the end you will have a full 3D component. So the interface between this digital layers and the physical layers is the additive manufacturing. It's an umbrella term. It comprises of many different technologies. Here, what I have shown is a so-called dedicated energy deposition (DED) process. When I'm talking metals, there are normally two processes I'm talking about. One is a so-called laser powder bed fusion, where we have a bed of platform, a powder bed, and I shine a laser from the top. And this laser follows a tool path given by the machine. And wherever the laser flows, I create a small melt pool and melt the material. In a DD process, I melt the material and I blow the powder along with the laser into the melt pool. So this is but this is not the entire picture. It's more like this. Everything in LPBF is at least 10 times smaller. So the laser spot size, the melt pool dimension, the layer height, everything is at least 10 times smaller. But also the process speed is slow. But when I go to DD, everything is 10 times faster, 10 times larger, except for cooling rate, which is here much slower than it is in LPBF. This a major share of the market is of course LPBS, so we look closely into it. Here, normally we have a powder supplier. I raise the powder supplier at every bill. I deposit some amount of powder on a build platform. I shine a laser from the top to melt the material, which gives me the build part, and I repeat this process over and over again until I have a full 3D component. Basically, the increasing interest from the industry in making these alloys, which are traditionally considered hard to process in AM. So we have growing interest in tungsten, copper, molybdenum, aluminium, basically the entire arena of high conductivity alloys. We have again in the past we had a symposium just on alloys for additive manufacturing in 2019. There was one supposed to happen in 2020, but of course it did not. Objectify, the host of this series, they recently launched a copper alloy again in collaboration with us. So there is growing interest in making new alloys and making high temperature alloys out of AM. And which brings us to the motivation for this talk, which is there's a need to develop more predictive approaches to process parameter development. Trial and error is too slow and is too expensive. We need to move towards using simpler approaches, more predictive approaches. So let's begin. Um, just to make sure that we all are speaking the same language. These are some of the process. These are the things what we mean when I say process parameters. There's hat spacing, which is the distance between the two scans. There's point distance, so distance laser moves when it is shining and when it is, it shines, turns off, moves, and shines again. This is for the pulse laser system, which is the Renishaw system. I'll come to continuous laser system, which is most other systems. Then we have exposure time, We have layer thickness, so how low the platform moves after every layer. Then we have, of course, a laser power. For continuous laser system, point distance and exposure time, of course, are clubbed together in one variable, which is velocity. And then we have a maximum separation PS, which is just a geometrical factor. State of the art for process parameter development, as I said, is trial and error. We try, we make matrices, and we try. Design of experiments, some are using a bit statistical, but again, largely trial and error. It is expensive, requires a lot of powder, requires a lot of machine time, and time consuming. I need to make a lot of samples, cut everything, see everything. It's a lot of labor. Um, Another method which many people are using is the so-called volumetric energy density. It's very simple, very easy to use, but sadly not very predictive. What it gives me is basically very fundamentally energy input over volume. It does not take material properties into account. So if I have energy density for copper or steels or titanium, I cannot transfer it to molybdenum or aluminum or some other material. So this is useful, but only in a very limited span of materials. It does not take material properties into account. Another more advanced approach is a so-called normalized process maps. This does take material properties into account. So we have a rho density, CP heat capacity, melting temperature, and of course ambient temperature. And using this, I can make such normalized process maps. Uh, where you see it gives me a range. It gives me a range below a certain value. I have very low energy density, normalized energy density, and above a certain value, I have very high energy density, which of course leads to effects like balling, pinholing, etc., etc. But the window I get from here is a bit too large. You see, we have everything between 4 and 30. So this is a large window, and I need something more predictive to find my way in this huge jungle that this brings me to. Which brings us to this. Let's take a closer look at when things will work and when they will not. So when I'm making scans, when I'm making anything in AI, I'm basically making line scans, and then I go ahead and I make another line scan next to it, and these two scans overlap with each other, and this minimum overlap depth is what I'm calling as d int here, and of course then I have a layer thickness, the amount my platform is going down, and very logically, if my layer height is greater than my d int, I will always have a porosity here, right? So to get a dense part, theoretically speaking, my interaction depth or my overlap depth has to be larger than my layer thickness, but d int should be greater than n. Based on this, I can define a sort of a parameter, just a very easy dimensionless parameter d star, which is d int over L, and I can say that theoretically d star should be greater than 1 for complete melting. If this is not there, I will never have a fully dense component. Now d star is a function of melt pool depth, and then just simple geography, p, h, and l. So point distance, hat spacing, and layer height. If I'm using continuous laser system, p goes away, so it's just rm, h, l, n. Melt pool radius. This we can predict using very simple analytical models. So models which were basically developed for welding in the 1980s. This is a simple heat transfer model, heat transfer equation, and to get an analytical model, I need to simplify it to 2 or 3 variables using boundary conditions, simple boundary conditions. And this is what I need to be aware of when I'm selecting an analytical model. I need to check if the boundary conditions are valid for that particular system. For most systems, this works. This is a so-called 3D Rosenthal solution. It assumes a point-size heat source moving with a constant velocity over a semi-infinite surface. What does this mean? That my beam radius is very small compared to the distance the heat can diffuse through during the interaction time. Or this is the formula here. Don't have to worry about it. It's not very difficult. You need to plug in once. I can modify this for the pulse laser system. I don't think many of you are interested in this, but just in case. And this works. You see, this is what we get for molybdenum sample. This is the actual reading for the melt pool dimension, and this is the calculated radius from the Rosenthal solution. I would say it's not too off. Um, Okay, so let's get back. There is a factor there which was the laser absorptivity, which is very, very important. And yes, I can also measure it, just experimentally, but I can also predict it when I'm working with a completely new material. And this is basically related to the resistivity of the material and wavelength of the laser. This is a machine constant. This is very easy to measure and also get theoretically or from theory, from papers, from literature. And then I can plot this. So this is there is a very strong relationship between this laser surface laser absorptivity and laser absorptivity of the powder. The powder laser absorptivity is always a bit higher than on the flat surface because of multiple reflections. Uh, a lot of theory here. Let's get to some pictures. So we see high conductivity metals here behave very differently from low conductivity metals. So here you see my maximum depth is achieved almost where my laser is. Here it takes some time because the material needs time. The heat needs time to diffuse through the material in these materials. So my laser is here and moving there, and only a few seconds, a few microseconds later, will the melt pool reach its maximum depth. So the melt pool has a longer duration, a longer time. There's a lot of time available for it to flow and solidify and wet the surface. Here that's not there, which is why it's hard. I get. Okay, let's get to some applications. Just remember one thing: my D star needs to be greater than 1. And I show you here some examples where I keep the layer height constant and I keep the hat spacing constant. And I'm using only two variables: laser power and scan velocity. And I show you the energy density I kept is constant. How do I keep the energy density constant? I'm just keeping the ratio of power and velocity the same. I can keep the volumetric energy density constant. And you see, with the same energy density, but when D star is 0, I don't get, I get a shitty product. But when my D star is greater than 1, 1.7 in fact in this case, this is where I have a very nice project with very, very low porosity. If I were to plot these results, you see that these three lines, they are all with constant energy density, only changing the ratio of power to velocity, scan velocity. And I see that I can get only highly dense components, meaning more than 98% density here. And this is pure aluminum. This is more than 99.5% pure aluminum. I can only get pure, highly dense components when my D star is greater than 1.3. And everything else, no matter the energy density, I get a lot of porosity. Of course, this is not everything. Friends here know that there are many other things going on. It's not that simple. I can have balling, so which is when the molten material does not completely wet the substrate or the previously solidified material and forms these balls, globules. I can have residual stress cracking. I can also have keyholing effect. So this is when I have too much power and I start to evaporate stuff. And to take this into account into the simple analytical model is a bit hard. And there I mix it with statistics. I will show here some examples of pure molybdenum. So here we see just using simple DOE approach, I can see there exists an optimum exposure time for the material, and then similarly I can find out values for an optimal point distance. When the point distance is too low, I start getting residual cracking. And using all these things together, and going back to our fundamental and maximizing D star, we were able to reduce the porosity to less than to almost 2.5%. So producing components more than 97% dense for pure molybdenum, that is good density. In less than, I think this was 9 or 10 experiments, 9 or 10 different parameter set. So very, very quick, very, very fast. So concluding, finally, analytical models do work. They give you a very precise, not a very precise, but they give you a relatively well estimation of the melt pool size. You can use this melt pool size into a model to calculate D star, and just keep in mind D star greater than 1. And when you keep D star greater than 1, you will have a nice dense component. Of course, you can include certain factors of safety, so you can keep 1.3, 1.5, or whatever works for your material, because there is an error coming from laser absorptivity largely. And then there is more. You can use this approach to give microstructural predictions for improving in situ alloying. Of course, we do not have time for all of this, but it does work. Here I show you some a flavor of it. So when the melt pool residence time increases, which again you can get from the analytical models, the standard deviation goes down. This is the deviation coming from in situ alloy. So when I'm blending the material and making the alloy in the machine. So with this thought, I would like to end my talk. Thank you very much for your kind attention, and I'm here for any questions, doubts, anything. Please feel free to reach out.
Thank you for the amazing session. Hope you have learned a lot from this session.